Good morning, everyone. Thank you for joining our workshop on tri-generation systems based on heat pumps with natural refrigerants and multiple renewable sources. We have quite a packed agenda today, as you can see on the slide here, with a bunch of brilliant speakers. And we've aimed to bring expertise together from different fields. On one hand, on the engineering side and the technical side of things, we have expertise from social sciences here today, and also policy experts based in Brussels in the audience. So what we will first do is we will start with a brief presentation on what the 3HP project aims to do, and what the essence of what tri-generation systems are. This will be followed by 6 compact innovation pitches. The speakers are really good at presenting it, and they will bring it in a convincing manner. And then afterwards, this will be discussed with the members of the jury who have outstanding experience in the HVAC systems, who I will introduce in a bit after the first presentation. We will ask them for their feedback on what they on their thoughts on the innovations, and after that, also the audience will have the opportunity to ask questions to the 3HP partners, the consortium, about the presentations and the innovations of tri-generation systems within 3HP. So now I would like to introduce the first speaker. This is Dr. Danielle Carbonel, who will be representing 3HP.
So thanks everyone for being here today. I will give a very short presentation of the project. Basically, this will be a summary of what is coming next. We have 6 pitches, and it will be about all the things that I will comment superficially here. I'm the coordinator of the project. Here we can see the partners of the project. This is a research and innovation project in H2020, and we are in the last year of our duration. The idea of the project was to develop technologies from tier 3 to 5, which means that by beginning of next year, we will finish the project and we will be ready to go to the next level, which will be a real demonstration. We still need one step before going to the market, and we brought the technologies to be ready for the next step. So the goal of the project is to develop 3-generation systems, and by this we are meaning that we are providing heating, cooling, and electricity. And we are doing so by using electrically driven natural refrigerant heat pumps coupled with photovoltaics. And we are targeting residential buildings, and in particular, multifamily residential buildings. Our measurable targets are to achieve 80% of renewable on-site share with the concept of net zero energy building, which means we produce as much energy as we need, but we need to change 20% with the grid because we are lacking a seasonal storage. And by design, the systems we are developing and we are proposing have a low investment cost, or at least lower than a conventional equivalent system based on heat pumps, and we are aiming at cost reductions between 10 to 15%. And all this will lead to reductions on emissions up to 75%. So our target is both new and refurbished buildings. So the main difference, as you know, is new buildings, they have a higher share of domestic hot water, and all buildings that will be refurbished will have a higher share on space heating, plus a bit higher supply in the temperature. And for this, we are developing 2 types of heat pumps. Propane heat pumps are targeting refurbished buildings, and CO2 heat pumps are targeting the new buildings with a large share of CO2 of domestic hot water demands. Of course, we need to also cover electricity, so we are using photovoltaics and batteries. But the project in itself, it's not about developing any hardware on this level. We are using off-the-shelf components, and we are applying them on our advanced energy management system and our motor predictive control. There will be a presentation for this later on. And we apply this also in our system test, the way we test the systems with hardware in the loop, that will be also explained later on. So 3HP is aiming to develop 2 main systems. One is what we call a dual sourcing system. Basically, it's a system to provide heating and cooling for South European climates, where that is using borehole, so ground source and air as heat sources and sinks. There will be a presentation for this, so I'm not going into the details now. Second system is what we call a solarized slurry system. This is a system that it's mainly used in Central Europe to provide heating demands, with cooling as just an add-on feature. And it's using solar collectors as a source for the heat pump, with an ice storage as an intermediate source when there is not enough solar. There will be also a presentation for this. And all the systems are using an advanced energy management system with model predictive control, and you will also hear a presentation later on, so not going into the details. We also thought it was very important to consider acceptance. We know that unless technologies are accepted, they cannot be deployed. And we did quite some work in understanding and improving the stakeholder acceptance and identify the interest on the stakeholder needs. And there will be also a presentation later on this specific topic. And as a summary, I would like to show the key results of the project. Basically, we started to develop with materials. We developed isophobic coatings for the ice slurry system. We will explain a little bit later on this. These materials were used in what we call supercoolers, that are heat exchangers that are able to decrease the temperature of water in liquid form. And we have also developed two kinds of heat exchangers, dual sourcing, and a tripartite gas cooler for CO2 applications for a transcritical cycle. All this is done. And these heat exchangers were then applied into natural refrigerant heat pumps. We developed 3 of them, 2 propane, 1 for the dual sourcing system, 1 for the ice slurry system. These things we developed 2 prototypes, and both are tested and finished. And the only thing that is ongoing is the CO2 test for the ice slurry system. We also developed this advanced energy management system with fault detection. This is done, and now it's being applied on the lab, on a real system. And the ongoing task now is this hardening the loop of the complete system test, where we are testing the systems in real-like dynamic conditions. So that was the picture we could take at the beginning of the project. Unfortunately, then pandemic hit, and we have been meeting mostly online until just recently. Yeah, so that's a bit the summary, and you will hear now about the interesting presentations. Thank you.
Thank you, Danny. So now we will move on to indeed the next part, the innovation pitches, as I've shown earlier. We have invited 2 members of the jury. Sylvain Courtet from the president of Eurovent certification, who are world leaders in third-party compliance and certification of HVAC systems, and Jeko Volashikov, an environmental research engineer at Daikin Europe, from the Department of Product Legislation and Standards, with strong experience in research, testing, and optimization of advanced HVAC solutions. After the innovation pitches, we will ask for their feedback on how they feel is what the market position is of tri-generation systems, and what they thought of how the innovations could contribute to this. So now we will get right into the first innovation pitch, which is Michael Schubert on solar ice slurry systems.
Yes, I'm Michael Schubert, researcher at SPF. I'm presenting the solar ice slurry systems. How does it work? Okay. So solar ice slurry system is one of the 2 systems we are addressing in 3HP. As you heard before, it's more for the moderate or colder climates. We have ice storage combined with solar thermal collectors as a heat source for the heat pump. The solar collectors can also provide direct heat for the warm storages if the temperature level is high enough. And if it's lower, it's just loading the ice storage. The ice storage has some capability to provide some little cooling demands in summer, so enough for really moderate climates, but not thought for southern climates. And we are not using a reversible heat pump in this system. The heat pumps we're using in this system, you will see a presentation about that later. One is the CO2 heat pump, thought for new buildings with a high share of domestic hot water demand, and one is the propane heat pump, thought for the older buildings, the refurbished ones with lower share of domestic hot water demand. So solar ice system is kind of a, or solar combined with an ice storage is kind of an alternative source for heat pump systems if boreholes and or air is not wanted or not possible due to regulations or efficiency or similar things. And in principle, it acts in its long-term behavior like a ground source heat pump system with a full regeneration of the ground. And when we look to the costs, in 3HP we suggest not to use a conventional ice storage that has the heat exchanger within the ice storage, but a slurry storage. And this should reduce the costs of the overall system by about 10%. And so with this, we are in a range that is similar to the costs of ground source without regeneration, but it should be less expensive than a ground source system with regeneration. And regeneration is becoming more and more important. I will quickly show some results from a numerical study where we had the goal of looking for different climates all over Switzerland, or for different regions all over Switzerland, how this system works and how we have to scale it for reaching a seasonal performance factor of about 4. And there we ended up with a conclusion that we need about 0.6 cubic meters per megawatt hour ice storage size and 2 to 2.5 square meters per megawatt hour heating demand solar thermal collectors. And because these numbers are a bit difficult, I show here some examples. For example, for Bern, which is the capital city in the center of Switzerland, we need about 15 cubic meter ice storage size for a new building and about 90 square meters collector field. And of course, for an old building, we have to size it bigger. For a new one, we can size it smaller. And regarding the cost, this is one example with a comparison between the solar ice system and the ground source system. And we have the heat costs per kilowatt hour here. And we see that the solar ice system, but this is assuming a conventional ice storage, is a bit more expensive than a ground source system without regeneration. But with the ice slurry storage, it should be reduced by about 10%. And just as an outlook, currently we are testing this system and also the other system, the dual source, dual sink system that Laura Alonso will present afterwards. We are testing those in a concise cycle test, so in a hardware in the loop test. And, oh, sorry. Can I go back? You can see here a sketch of such a hardware in the loop test where everything what is in the blue part, so with the blue background, is really installed in the laboratory, so the whole system is installed, it is controlled autonomously, it is running autonomously, and parts that are interacting with the environment or with the building, like the space heating, the PV modules, the thermal collectors, all this is emulated. So everything that is here shown in the gray part is simulated, emulated. And if you have interest in this topic, I will present this later in the CO2 energy session at about 10 to 3.
Thank you, Maaike. Now we will have a presentation by Laura Alonso from the Development and Research Institute of Tecnalia, based in Spain, on dual source system.
Okay, thanks. I am Laura Alonso, researcher in Tecnalia, and I will give you an overview on the second system we have developed in tree heat pump project, the dual source system. So starting the background of what's this technology, hybrid systems are an innovative alternative to either aerothermal or geothermal heat pumps, meaning they can use both sources or sinks for the heat pump. And normally a geothermal heat pump is used where an additional heat source or rejection heat exchanger is added to the system. And so these systems are useful especially when buildings' heating and cooling demands are not well balanced. For example, in cooling-dominated climates, they can avoid excessive heat rejection to the boreholes, and so the borehole length can be reduced. and so the investment cost is reduced as well. And in heating-dominated climates, they can mitigate the ground temperature decrease, an excessive decrease, and so they can improve the ground source heat pump operation. Normally, the commercial systems use, as I said, geothermal heat pumps plus dedicated air-to-water heat exchanger, external heat exchanger. Some research has been done on dual-source heat pumps, and this research is mainly focused on parallel systems, so systems in which a parallel heat exchanger between the refrigerant and air and the refrigerant and water or brine is included. And normally what's claimed in the literature that it's difficult to control the amount of refrigerant distributed among both circuits, so these systems are kind of difficult to optimize and to operate. And in other sources of the literature, COP increases of up to 88% were claimed at system level. So this lead to high reduction in investment cost and operating costs. So what is three heat pumps approach for this dual source system? Well, the main innovation is the dual source heat pump. The dual source heat pump used for heating and cooling. So it is a reversible heat pump, and it's using geothermal and aerothermal energy as a source or a sink for the heat pump. And the main innovation is it's using a combined evaporator condenser with air, brine, or both at the same time in a unique device, in a unique heat exchanger, the so-called the dual source heat exchanger. The heat pump is using a natural refrigerant, propane, and it's integrated in the system, including photovoltaics and electrical storage for the heat pump and for household electricity demand. And the same way as the other system is governed by an advanced energy management system. Okay, this is an overview of the heat pump included in the building's thermal system. And so it can work in heating mode using air, the fan here, brine from the geothermal boreholes, or both at the same time in order to provide the space heating and domestic hot water. It's reversible, so it can work also in cooling mode, the same as in heating mode with air, brine, or both at the same time. And the system can also provide free cooling by exchanging heat directly with the boreholes. And the system is controlled for making a choice in using the air or brine, and also for the free cooling control. So research activities we have been developing with this dual source system. First of all, the definition of the system configuration and working modes. Then the design, construction, and testing of a dual source heat exchanger and heat pump. This is the, sorry. This is the dual source heat exchanger that will be explained later. And for the dual source heat pump, we have constructed a first prototype with bare tubes and a little more complex refrigerant circuit. It was the first one. We have tested it, and then we built also a second prototype, which included enhanced tubes, and also the refrigerant circuit was optimized. So this allowed us to reduce the unit size and also an important refrigerant charge reduction. Also, system is simulated and tested. This is ongoing now. And finally, extrapolation of the simulations for several European climates will be done. Okay, so which are the advantages of this three heat pump system? First of all, for the use of the dual source, we can reach a reduction of the borehole length by an estimated 50% when compared to ground source heat pump with the same efficiency. And we believe it can lead to between 15% and 20% lower investment cost on the complete system. And also it's using natural refrigerants. As said, well, this is used more and more each day due to regulatory issues such as the F-gas regulation. So we have requirements now for low global warming potential fluids. And so the use of natural refrigerants is spreading in cases where it is technologically safe and economically feasible. And in this case, in the dual source system, propane is used as a refrigerant. Thanks.
Thank you, Laura. And I will ask Daniel to come back to the front to present on a broader scale the advances in heat exchangers.
Good. So I will now explain a bit the three kinds of heat exchangers we have developed. So we have two kinds of heat pumps, and these heat pumps need innovative heat exchangers. And I'm going to show you this kind of three innovations. One, it's focused on the ice slurry approach. And I just want to show quickly, this is a traditional ice storage, what is called ice on coil. This is something that is being constructed. At the end, tubes are everywhere in the storage. So this has a high cost of construction and material, and that's why we are aiming to delete and eliminate all these heat exchangers. So an ice slurry system is a vessel like this one without anything in. And this reduces the cost dramatically on this part, which is a key aspect on this kind of system. And this has the benefit also that can be used for refrigeration applications. We are applying this to heating, but it has a higher potential even for cooling applications. So we said, okay, we would like to use a slurry, and what exists today as a slurry is what is called an ice scraper. So basically you have a very cold surface where ice is built, and then there is a rotating machine that scrapes ice from the surface and produces a slurry. But these things are very expensive, need a lot of maintenance costs, and therefore they are not really deployed in Europe, despite the fact that they exist commercially. So what we propose instead is what is called a supercooling concept. And supercooling is a simple idea, difficult to do in practice, which is we take water, we cool it down below the melting point of water, and at some point we cool it further until we disturb water in what we call a crystallizer, and then ice slurry is produced, the latent heat is released, and then we have this slurry flow. And the difference between the melting point and the actual crystallization point is what we call the supercooling degree, and the higher the supercooling degree, the higher the probability of freezing. So in order to achieve a stable and safe supercooling degree, what we did is we developed isophobic coatings, so coatings that are able to delay the formation of ice, not eliminate it, but delay it. And these coatings have been applied in brazed heat exchangers on commercially available heat exchangers, and we have tested this in the lab. Now, I don't have time to go into the details of these results. I will just focus on, this is a reference heat exchanger, so this is a commercial heat exchanger without any treatment. And let's now just look at, for example, HOIS-2. This is an hybrid organic, inorganic, silane soil gel coating developed by DTI. And this coating is able to reduce the outlet temperature of the supercooler by 40%. It means that in average, this is the different results on the experiments. We did several testings. And on average, we were able to achieve -4 degrees water in the outlet of the heat exchanger in liquid form. Second heat exchanger we developed was a 3-parted gas cooler. That's necessary for CO2 applications with a transcritical cycle. For those that are not on the CO2 side, I would say a gas cooler is an equivalent of a condenser. The difference is that in transcritical CO2 cycles, the CO2 is not condensing, but it's having a large delta T into the gas cooler. And this means it's very good for domestic hot water applications where you can have water heated up from 10 to 60 degrees, but it's not good for space heating. And then NTNU developed this heat exchanger, a 3-parted gas cooler that is able to follow CO2 very well with preheating domestic hot water, providing a space heating, and providing reheating of domestic hot water. So this increased efficiency significantly when operated in parallel, plus can provide space heating demands. And what existed before 3HP was this, also at NTNU. It is a lab thing, custom made, and now they made it using plate brazed heat exchangers, and they were able to reduce the weight by 80% and the area significantly. So the third heat exchanger is what is used in this dual sourcing. And the main innovation here, I mean, this is the kind of the heat exchanger, which is basically a coaxial tube, where in the annulus there is the refrigerant, inside it's the brine, and outside there are fins, and there is air blowing on it. And the main innovation is that there is a direct exchange between the heat transfer fluids and the refrigerant, and that's why this heat exchanger is quite efficient. And so Tecnalia developed this. This is one of the prototypes, and they developed two kind of prototypes with quite an improvement from the first to the second. The second one has these corrugated things inside the tube to increase heat transfer coefficient. And they were able, with their measures, to reduce the internal volume of the heat exchanger from 15 liters to 5.5. This reduced the surface area from 112 to 54, and of course then the refrigerant charge was reduced significantly. Thank you very much.
Thank you, Daniel. Now, for the next presentation on heat pumps with natural refrigerants, Alireza Zendeboudi from Norwegian University of Science and Technology. Alireza, the floor is yours.
Yes, thank you very much. My name is Alireza Zendeboudi from Norwegian University of Science and Technology, based in Trondheim, Norway. And I will present the slides for the heat pumps with the natural refrigerants today, covered by the 3HP project. I'm getting back actually to the fundamental question, why the natural refrigerants actually. So here actually in these slides we have the development for the refrigerants, starting from the first generation here, which actually we use the natural refrigerants. And later the second generation introduced CFC and HCFCs for the concept to be safe as a replacement for the ammonia, which was really popular at that time. However, after a period of time using, we faced actually with the problem with the ozone layer. So the third generation introduced the concept for the HFCs, which continued by around 2010. As a replacement for the ozone layer protection, we found actually the problem with the global warming, and recently the fourth generation HFO actually introduced to avoid the global warming. However, the consequence is the impact on the human health. So with the advanced actually technologies, the researchers getting back again, working on the natural refrigerants such as CO2, ammonia, water, propane, and so on and so forth. So we do believe that only the use of natural refrigerants for the heat pumps can be considered as a long-lasting solution, and that's what we need actually to focus on for the sustainable environment, sustainable actually technologies. All right, so through 3HP project, as my colleagues mentioned, we developed three natural-based refrigerant heat pump systems. So the first actually prototype is based on the CO2 refrigerants for the buildings. When the domestic hot water is dominated, we utilize the concept for the auxiliary system, the tripartite gas cooler to improve the efficiency of the unit, and also we utilize the ejector technology to reduce actually the compressor work and also recover some of the losses that we face actually. So the second prototype is based on the propane refrigerant when the space heating is the matter inside of the buildings. We develop actually two different types. So the first one based on the propane is based on the ground source, and the second one is based on the concept of auxiliary or the evaporator supercooler, which I explain actually later a bit. So here we have actually the concept for both of the heat pumps which develop under the 3HP. So the first one is based on the auxiliary, as you can see here on the left side. Here we have actually the heat pump, the auxiliary, and also the demand for the heating and cooling. Of course, we have the PV, solar thermal, and advanced actually control strategy. And on the right side, you have the concept for the dual source heat pump system, where we have actually the heat exchanger here, heat pump, and also the demand here, as you can see it here. All right, so the first prototype is the CO2 ice heat pump system. Here we have the figure, the schematic for the heat pump. So we use actually the tripartite gas cooler. Why? Because we were able actually to combine the domestic hot water and space heating functions together. We were able actually to improve the temperature match between the CO2 and water, which results into the improvement of the efficiency of the system. And by using the brazed plate heat exchanger, we were able actually to make a compact and high efficient system. We tested actually the heat exchangers at Antony University, and finally we built up actually the unit in Switzerland. But how the system works? The high temperature, high pressure refrigerants getting out of the compressor passes through the tripartite gas cooler, comes inside of the internal heat exchanger, ejector, evaporator, separator, and then going to be the suction inside of the compressor. On the other side, into the counterflow, we have the domestic hot water inlet temperature, the tap water around 10 to 12 degrees Celsius, going to be preheated actually from 10 or 12 to, let's say, 40 degrees Celsius. And also going to pass through the gas cooler 1, which going to reach to up to 65 to 70 degrees Celsius, going to be supplied to the temperature. For the gas cooler 2, we have the space heating inlet temperature and outlet, which is going to be under design condition 30 degrees Celsius, and the outlet is 35 degrees Celsius. So the system is able to work only on under the domestic hot water operation, only space heating, and also is able to work under the combined mode to have the domestic hot water and the space heating at the same time. The second prototype is the propane ice heat pump system. The system also is able to work under only the space heating, only domestic hot water, and also the combined mode. Here we have the schematic actually for the unit. The inlet of the desuperheater is the outlet of the compressor. Passes actually the refrigerant through the desuperheater and also the condenser, and goes actually to the evaporator. We have actually the counterflow here. This is the concept, only the green one when we want to use the system for the domestic hot water production. We use the condenser for the preheater and the desuperheater for the reheater for production of domestic hot water. And here on the left side, we have the schematic when we want to use the system under the combined mode or only the space heating. We're going to use the condenser for the space heating production, and on the combined mode, we use actually the red one for production of domestic hot water when it's under the combined mode, actually, the system. The last actually prototype which we developed is the concept for the propane, but this time with the dual source heat exchanger. I do believe my colleagues explained the concept for the dual source heat exchanger. However, the system actually is able to work under the cooling mode and heating mode. Here we have the schematic for the heating mode, as you can see here. Again, the high temperature, high pressure actually refrigerants getting out of the compressor passes through the desuperheater, which we can use actually for production of hot water, goes through the four-way valve, and from here, the system operates depending on the demand. So, for example, under the heating mode, the dual source heat exchanger working as the evaporator, as you can see here, and our actually the space conditioner heat exchanger working as the condenser. So the refrigerant actually after the four-way valve is sent to the space conditioner heat exchanger, passes through the evaporator, which is the dual source heat exchanger, and then going to be the suction for the compression, and then we have the cycle. In this slide, we have actually the system, the propane dual source, but this time working on the cooling mode. So for this time, actually, after the four-way valve, the refrigerant is sent actually to the dual source heat exchanger, which works as a condenser this time, and our space conditioner heat exchanger working as the evaporator. So in this way, actually, the system is able to work both on the heating and cooling. So we tested all of the units except actually the CO2 ice. We tested under the first prototype. We developed two prototypes for each system. We designed, we built it up, tested. We found actually the problem, and then we went actually for the second prototype to see how we can improve and optimize the performance of the unit at the end. All right, thank you very much for your attention. That was the main concept for the heat pump, and I hope it was interesting. Thanks.
Thank you, Reza. Then on to the next presentation on the advanced energy management for trigeneration systems, which will be presented by Thibaut Péan from IREC de Catalunya Institute for Energy Research, based in Barcelona.
So, good morning, everyone. So, yeah, I'm from IREC in Barcelona. I will present this advanced energy management for the systems that were presented before. So, not to repeat again, but these two types of system were presented before. So, they both, so the dual source and the solarized, both have different energy sources, different storage. So further than only the innovations of the heat exchanger and the performance itself of the systems, we also need advanced management and control to further improve the overall performance of these whole systems. That's why we have developed these smart controls that can act on the different parts, so whether the loads, the storage, the sources, receive information from them, and also interact and send control actions to them. This comes from identifying some challenges that heat pumps are not always used optimally, can result in high electricity bills. Also, the maintenance could be not always very often done, so they operate sometimes below their design efficiency. And they can create also peaks of electricity consumption if we have a very high rate of penetration of heat pumps. So for this, we have developed these two algorithms within the 3HP project. The first one is the optimal energy management. Its goal is to minimize the energy cost and also increase the share of renewables used in all the systems. And the other is the efficiency drift self-diagnosis system, which is aimed at facilitating the maintenance and increasing the reliability. So both algorithms are independent, but we consider them together as algorithm for the management and control of the heat pumps. So they are fed with different things such as the sensors and forecast of weather, occupancy, and prices. So getting a little more in details about the advanced energy management system, it's structured in two main modules. We have this central controller, which is the core of it. It includes an optimization problem on 24-hour horizon, fed with a different forecast and measurements. But this is updated every 15 minutes, so also we need a local controller, because it can happen that within these 15 minutes, some things unexpected happens, especially with the electrical part that is varying very frequently. So we need a local controller to also adjust the set points that come from the central controller in real time. And a little bit more details about these functionalities. So the EMS makes use of 24-hour forecast of the weather, occupancy, and especially energy prices that vary hourly. And of course because it's model predictive control, so it needs models, simplified models of all the involved systems. So we have also developed all these simplified models, mainly RC models, that enable to project the behavior of the systems in the future, and also is fed by measurements from the sensors. And it uses all this to solve the optimization problem every 15 minutes and create an optimal planning of the resources. So, for example, in the case of the dual source system, to choose the most efficient source at every moment, because it knows the performance depending on the temperatures of these both sources, to anticipate the cheapest hour for charging the electrical battery. Of course, this maintaining the comfort at the desired boundaries. But the overall goal is to reduce the costs by shifting the thermal loads to the cheaper hours, because it's a cost-driven optimization so far. And by doing that, since we have also solar energy, it also optimizes the use of renewable energy sources, because since you have free available energy, then the optimization will tend to optimize its use. On the other hand, so the fault detection and diagnosis algorithm is aimed at detecting some common faults, such as evaporator fouling, compressor valve leakage, liquid line restriction, and refrigerant overcharge, for example. And we are trying to detect the degradation of the COP for this type of variable capacity heat pumps. The goal is to detect efficiency drift of at least 10%, using sensors already available in the heat pump, so not adding any additional sensor. And then the algorithm creates alarms and diagnoses the fault. We have tested this in both in simulations and in laboratory experiments, so we can see the COP that we emulating the faults, the COP that drifts over time, and we're able to detect that. So just shortly, some overview of some results that we have obtained. So with the energy management system, here you see the energy imports of reference control compared with the energy management system, and highlighting the periods of high prices. So with the energy management system, we concentrate the imports and the periods of cheap electricity, leading to cost savings of 11 to 47% in the case that we have studied, and increasing the seasonal COP thanks to this knowledge of the performance in different conditions. For the fault detection, we are able to detect this COP drop from 7%, which is quite satisfactory, and to diagnose every fault except for the evaporator fouling. And here you see some graphs showing the degradation of the COP in function of the intensity of the different faults that we have tested. So this is a bit an overview of the performance that this algorithm can bring further than just the systems in themselves, so how to optimally manage them. So thank you.
Thank you, Thibaut. Now we'll go into more the social expertise, the social sciences expertise on the social acceptance of 3HP systems by Thomas Friedrich from the ISO Institute for Social Ecological Research based in Frankfurt.
Yeah, thank you very much. Hello, everybody. So I'm going to give you the last presentation on social acceptance of 3HP systems. My name is Thomas Friedrich from the Institute for Social Ecological Research, and together with my colleague Emanuel Sties, we are from this institute that works very interdisciplinary. So we are social scientists, but we also work together with natural scientists, with engineers on several topics and research areas, as you can see on the left. And we also work together with practitioners and stakeholders, because we are convinced that they have to be involved in the research process. So very interdisciplinary and transdisciplinary. So what we did in this working package on social acceptance of 3HP systems in the project was to try to better understand the potential non-technical impacts of those systems by identification of the interests and needs of key stakeholder groups, by the exploration of market safety and regulatory barriers, by determination of the benefits and incentives to overcome those barriers, and by identifying geographical, legal, and cultural differences. So what we did was to do in-depth stakeholder interviews with what we consider to be key stakeholders, and national stakeholder workshops in 4 countries, which is Germany, Switzerland, Spain, and Norway. The stakeholder groups that we considered to be key stakeholders were investors of multi-family buildings, architects, manufacturers, heat pump manufacturers mainly, engineers, HVAC planners, technical consultants, representatives from associations, and heating installers. The topic that we were focusing on in the interviews, as also in the national workshops, were focusing on renewable heating and cooling based on electrical heat pumps such as 3HP. So what you can see here are 2 reports that you can find open access on our Zenodo community, 3HP community. You can also find all the other reports from my colleagues that presented before, there. And the left one is about the interviews that we did before, and the right one is about the workshops that were based on our results of the interviews. So, of course, I cannot go into detail about all the interviews, but let me give you some key results that we had, that we found out in our interviews, in our stakeholder interviews, that were mainly about finding out what are the barriers and drivers of 3HP systems, meaning complex renewable heating systems based on electrical heat pumps. So there were some crucial topics that were discussed in those interviews. You see some categories here. It was, of course, about economic efficiency, but it was also about simplicity, about complexity or simplicity of those systems, about practical feasibility, about competence and skill of those who implement those systems, about cooperation of all the different trades that are involved on the building site, and of course about public support. And we found out that contexts matter very much. We did these interviews in various countries, and there is differences nationally, climate differences, but also legal differences, but also regionally, if you think about the different cantons in Switzerland or the autonomous regions in Spain, and also locally differences. However, there are some common features, like heat pump systems call for higher skills on the part of planners and installers, especially in existing buildings. There is a need for improved standardization and harmonization of funding and approval processes. And heat pump systems call for a challenge of existing, well, they challenge existing business models, especially in the heating sector. And especially the heating sector was mentioned very many times in the interviews and later on also in the stakeholder workshops. Apparently they were kind of the bottleneck of the implementation of those systems. So we took those interviews from the interviews into the stakeholder workshops. We invited representatives of key stakeholders into workshops also in the 4 countries, Germany, Switzerland, Spain, and Norway, and discuss those results with those experts. So the important transnational challenges that were identified in those workshops were investment upfront costs, but also the high planning and coordination effort of those systems, and again, the shortage of skilled workers. What you can see here on the right is a picture I just took a week ago in a German city. So it's funny for those who don't understand the German subtext and subtext. It's meaning like heating with oil set for the future. And this is a heating business, heating and installing business, and kind of symptomatic to what we found out in the interviews and also the workshops. So this is their business model. This has been their business model so far, very successfully, and yeah, this is going to change. We also asked in the stakeholder workshops about key actors that can drive solutions. And the most mentioned there were building owners, because they make the investment decisions, HVAC planners, and again, the heating installers. And finally, we asked for suggestions for solutions, so what can be done to overcome those challenges that have been identified together. And among others, you can read here, it's that economic efficiency of heating and cooling systems should be considered over the entire life cycle, that there is a need for more support of new business models, such as energy contracting, that there's a need to simplify those systems and to provide easy-to-use planning tools, and yeah, last but not least, new finance and funding schemes are important. Thank you very much for your attention.
Okay, thank you for the nice innovation pitches and the presentations, and thank you for nicely on time. Now we go on to the next part of this workshop, which will be a discussion with the jury and with the audience afterwards as well. So as mentioned, as presented earlier, Sylvain Cortet, the president from Eurovent Certification, and Željko Blašikov from Daikin Europe will be part of the jury. We had a third jury member, Jaap Hoogling, but unfortunately, as is the times, he had yesterday he mentioned he had COVID, so yeah, there's a could not make it. So for practicality speaking, I would invite Sylvain and Željko to come to the table maybe, to easily speak. And so just your feedback on the tri-generation systems innovations, and maybe if you have questions. And afterwards you can, the consortium can try to answer any feedback, and we can also allow questions by the audience and afterwards. Sylvain, maybe if you want to start. Thank you.
Okay, thank you. Well, I would like to thank all the people who presented those very nice and very interesting presentation. It's very impressive, the work that has been done. I would say that I'm quite confident that the science community is able to produce very nice, innovative solutions, and that on the other side, the industry is able to produce such very good products. My concern, and this is related to the very last presentation, is the fact that these systems are very complex, even more complex than heat pumps, which today are difficult to implement, like simple heat pumps, compared to traditional gas boilers. So it's very interesting that the last presentators show what were the barriers. And to me, what is the most important and maybe the most critical barriers to implement that massively are specifically the people, skilled people, to design, to install, and to maintain those products. So really, I would like to emphasize on that, because today it's mainly one of the most critical problems that we would face in order to implement those very nice solutions in the future. So yes, I think it's very interesting to look at it, and I don't have the answer to this question, but I think we really have to ask ourselves how we will manage to educate those people so that they will be able to provide those solutions.
Thank you.
Yeah.
Go ahead, sorry.
Another comment is regarding the natural refrigerants. We have to be careful for some of them, like propane can be dangerous, and it's related to the first item. We have to have skilled people to manage that. So this morning, Paul said that we are in an industry that can kill people because of indoor air quality, but actually propane in those kind of units could be also very dangerous. So we have to be very careful of how we would manage those products. That's the first point. And another point related to CO2 products, maybe we'll have to manage and to see if they are efficient enough to be compliant with current regulations. We have eco-design regulations today. They were based on traditional refrigerant. Would CO2 units be compliant, especially on the cooling side, with those regulations? So there is a trade-off between natural refrigerant on one side and energy efficiency on the other side. So that's also a complex subject. Thank you.
Thank you, Sylvain. I'll give the floor now to Željko Blašikov from Daikin Europe on your feedback and if you have any questions.
Yeah, thank you. Thank you very much for the nice presentation, and that it is a very relevant and interesting topic that you have researched, especially now with decarbonization and decoupling from the Russian gas. So it's become very important to find new innovative ways, and you are going that way, I can see. What is interesting for me as a question, I have divided here into different sections. The slurry ice the solar slurring system, you said that there is 10% less cost. Is this related to the reason because it's a slurry and has a lower density, per volume, or is it another reason that's why it's cheaper compared to conventional ice? You mentioned that in your presentation. What is the real site? And then you mentioned that it's not reversible. So are there any plans? Sorry?
Yeah, for the consulting
Yeah.
side.
So just to finish with that question, are there any plans to make it reversible as well? So if you can answer, and then I can go further down with my questions.
Danny, I think it's best that you come here.
So the reason why the ice slurry system is 10% cheaper is because the ice slurry doesn't have heat exchangers in the ice storage. In conventional technology, have heat exchangers in the storage. You need tubes everywhere.
Okay.
Because if you don't put tubes, so if you have a storage like this, you need to have tubes everywhere. Otherwise, you cannot extract the latent heat. Because when ice builds on a heat exchanger, the heat transfer coefficient drops dramatically. So you can only maybe ice a part of this from a tube. The rest is lost. And this reduces dramatically the cost. If we are going to make it reversible, not likely in this specific application, because this system is meant to provide mainly space heating demands, where space cooling is an add-on feature. And the thing is, if you make it reversible, you need a way to extract heat. You need to reject it somewhere. It's a water-to-water heat pump. It means our only way to reject heat would be via collectors. And they are uncovered and selective, which is not the best thing to reject heat. So it's not a system for cooling. It's a system for heating.
Okay, so you see only application for heating in that system. And have you tried to make, it's common question for all systems that you studied in your, have you tried to make like a life cost cycle analysis or life climate cycle analysis on the product? What is the impact compared to similar products using, for example, other refrigerants?
So the full life cycle analysis, I think we have not carried out. I don't know if you have it.
I've done it actually for the CO2 compared to, this is worth coming to this question. I have done actually compared to for the CO2 ice, compared to the electrical boiler over 20 years, of course, when it comes to the life cycle of the unit. So we were able, so not with the isolator, but CO2 with the ground source as example. So the payback started to be after, let's say, 9 or 10 years afterwards. So that's the start of the payback period actually for the heat pump system, but not with the isolator again, with the ground source heat exchangers.
Okay, so only for the one system was done. And also, you mentioned that such systems are difficult to control, and what is your intention towards that? Because, I mean, control, you say it saves energy, it can be more efficient, but if the control is too sophisticated, it can add up on the cost of the product in general. So such sophisticated control and different behavior of occupants in buildings, this can really create some issues.
Yeah. So the idea in the project was to analyze the potential of an advanced energy management system. You don't need it. It's something on top. I mean, we can go with rule-based control, it works. As soon as the control is well done, it's safe and it operates. I mean, these solarized systems are implemented in Switzerland, they are growing there and also in Germany. So these systems are already going on with traditional controls. Now, the thing is, if we get into a state where we'll really need to react on electricity prices, because the market will be using electricity prices for all, and we want to cut peaks, then this kind of model predictive controls will support us. But it's an add-on feature, it's not a must. You can go on with rule-based.
So then your savings, the calculation is based on savings from the unit itself, and it does not consider the control.
So the savings that were shown by Thibault, these are provided by the control itself. Yeah?
By the control itself, and not considering the consumption of the controllers.
Not the consumption of the controllers.
Okay, thank you. otherwise, it's very interesting. I mean, however, in some of your systems, you show that you have more heat exchangers than, one in the parallel connected or in series. Doesn't this increase the cost of the final product and the burden to it?
So in all heat pumps, we use the superheater, and this is something we could remove for a full-time or for a prototype that can be on the market. We wanted to see whether this was adding, and actually we realized it's difficult to control. If we go in parallel, going space heating and domestic hot water with the superheater, it's difficult to control, to have the set points. So we could actually reduce this. The tripartite gas cooler, it has 3 heat exchangers, but it increases slightly the cost, but it reduces dramatically the operation cost. So it really pays off, because with the CO2 you cannot go very efficiently with the space heating applications, and with this heat exchanger you can do that.
And this could be clearly seen from the life cycle cost analysis, or? Because you said,
Of course, so we consider the cost for the tripartite gas cooler, of course, inside of the life cycle analysis. Of course, it's going to add some value to the total cost of the unit. But I guess Danny presented the total cost for the heat exchanger, so it's going to be €3,000 for 10 kilowatt, which actually we develop here. So the total cost of the unit, we expect it to be something around, so let's say it's 6,000, 7,000, something like that for the production of the unit itself. Not using the auxiliary, like consider as the air source itself. But of course, you have to add the cost for the ground source or also the auxiliary system if you want to consider. But I have to point it out that we also did the analysis for the environment both in Norway and Switzerland. So using CO2 compared to the electric boiler, we were able actually to save up to 80% CO2 reduction per year actually in both places.
Yeah, but I think it would be also interesting, that's just my opinion, to have a life cycle cost analysis comparison to a traditional heat pump.
Yeah.
Air to air or air to water, so that you can see how these systems perform compared to that.
So, the aim of the project was to reduce 10%, between 10 to 15% investment cost of the systems compared to current technologies with similar efficiency.
Okay.
So we cannot compare a system that performs with the SPF of 4.5 with an air source heat pump. Of course, air source heat pump will be cheaper, fine.
Yes, okay, thank you very much. And another thing is, it would be interesting if you have tested the units based on the requirements of the regulation Lot 1, 813, the current regulation 2013, and the requirements set in the standard 14825, just to have an idea how much is your SUP or SER.
So the heat pumps have been tested in normal test standards, and they achieve very high COPs. Can you recall these numbers?
So I would say, compared to the state of the art, our 410A, which can reach temperature supply at 63 degrees Celsius. We were able actually with the propane ice to reach up to 70 degrees Celsius. Of course, depends on the evaporator temperature, but the COP was something around 3.6 something, if I'm not mistaken. So the COP, depending on the supply temperature, of course, and the evaporator temperature, for the propane, going to range between 2.8 to 5.5, I would say. But of course, for domestic hot water production using the propane, the COP is less, but we're at least able to reach to that. For the CO2, when the system working under the combined mode, the efficiency is the best, and the worst case is when we use the space heating. For the supply temperature of 70 degrees Celsius, depending on the evaporator temperature, I would say the efficiency is COP ranging between 3 and going up to 4.5, of course, depending on the operating conditions on the combined mode.
Yeah, thank you very much. And one thing for the social acceptance, yes, you mentioned that the basic barrier was lack of skilled workers and some national implementation and like restraints. Are you intending in some way to make more awareness, or is there a part of the project that kind of considers that to make like deliverables or make awareness, public awareness on local, national level?
Well, the results are what was given in the interviews and the stakeholder workshops. So, well, I'm not intending anything, but I mean, it will be very useful to have more awareness on that, of course, more awareness on investors who make the decisions of the investments, and also more awareness for heating installers to maybe qualify more for that technology. So, but even in countries, for instance, like Germany, where you have a high public awareness on renewable energies, it doesn't help itself. So it's just one part of the puzzle, let's say. But more awareness definitely would be a good thing, yeah. Okay. But there has to be other steps to be taken.
And one last question from my side. It was very interesting to learn about these things going on, and it was really inspirational. Are you intending to run the unit for 1 year, collect some data, then analyze, then see under more realistic conditions, like test setup or a house or something like that?
So as I said at the beginning, the project will end up with a TRL level of 5-6. So we test things in the lab with real life conditions, but with an accelerated test. So we are testing about 6 days. We cannot test a year. But now it's the time when we finish this to go to the next project, where we would need to implement this in a real building and do a real demonstration project. And that will be the next step, the natural next step. When this will happen, it will depend when we get the funding for it.
Okay, thank you very much. Good luck with that. I can wish you only. And thank you for the interesting presentation from my side.
Maybe because I thought we would discuss this at the end when you would. I want to ask or to try to reply your questions about safety and propane. Yeah? That's a social acceptance thing, and we have to also be aware that this is regulated. And heat pumps that have a higher threshold, a higher propane charge than the threshold regulated, they have a casing with a ventilation, sensors, and when there is if there is any leakage, this thing, it's pumped out the building. We are using also combustors going to 1,000 degrees in every house, and this could be dangerous, but the technology is made in a way that it's safe. Propane heat pump is the same thing. Yeah, fuel, it's also combusting, and we have it in every house. Yeah? We even cook with gas. So the thing is, if this is regulated and it's done in a proper way, it will be safe. And we shouldn't scare people. I mean, we have to be aware of it, but shouldn't scare people with this, I think.
Okay, on propane, I think, okay, we all have boilers in our houses, but I think the pressure of the propane in those heat pumps is quite higher. And I think it implies some additional requirements. So as we said that we need skilled people to install heat pumps, traditional heat pumps. If you add this additional parameter, which is safety, it has to be taken care of. And yeah, we are confident in the ability of the producer, of the manufacturer, to produce safe products, but then they have to stay 10 years, 15 years, 20 years in houses, and it has to be maintained properly, so we have to be careful about that.
Yeah.
Just want to mention that for propane, of course, it's A2 in the category. For CO2 is A1, so no problem for the. Huh? All right, but if you want to put it outside, then of course you can have any charge that you want. But for the inside, and we develop actually technology for the alarm and ventilation system. So if there is any leakage, then we have this actually technology to stop the operation of the unit itself. So just want to add this one. Thanks.
Thank you for the highly interesting discussion, Sylvain and Jacko. It was very interesting to hear. I think we have time. We're running a bit behind, but we can allow 1 or 2 questions from the audience if there are any. There, you can stand in the middle and ask a question.
Didier Coulon, International Institute of Refrigeration. Just about propane, is it possible to know what kind of range you expect regarding the charge of the refrigerants? Because one of the questions is the charge of the refrigerant, to be dangerous or not. And I still don't know what kind of level, kind of charge is necessary in your systems.
So regarding the charge, so with actually the brace plate heat exchangers that we develop, we optimize actually the amount of charge compared to the current actually conventional technologies available. So for 10 kilowatt propane ice, we're able actually to reach to 700 gram, which is actually a great development. And also for the propane dual source, we're able actually to reach to, for the second prototype, 1.7 kilogram. Which we develop actually.
How many kilowatts? Sorry?
10 kilowatts.
10 kilowatts for the second prototype. Okay.
Yes.
1.7 kilowatts.
For the dual source and 700 gram for the propane ice prototype.
Okay, thank you.
I can just add something to those that are interested that the IEC 6335-2-47th edition has been positively voted and it will be out at the end of June. So it gives some relaxations on A2 and A3 refrigerants. Yeah.
Okay, I think we can allow 1 more question from the audience, if there are any. No? Okay, then we move on to the, thank you, Sylvain and Jacko, for sitting, for giving your questions and feedback. It was very interesting, and also thank you for the audience. We'll move on to the next session. You can move back to your places.
Thank you.
We'll move on to the next session, so which is this more general discussion on the market uptake of heat pumps in Europe. But what we will do is we will have 3 brief statements by Brussels-based EU associations. This will be Volker Franz, the President, Director General of EPI, the voice of natural refrigerants in Europe, and representing also the heat pump sector. And Josephine van Besselare, Head of EU Affairs at the European Heat Pump Association, as a key actor in heat pumps in the EU policy. And then as last, Davide Sabadin, Senior Policy Officer at the European Environmental Bureau. We'll get into it well, before we get into that, you can join us on Slido. So what basically we are asking the question, what are the main barriers to the market uptake of heat pumps in Europe? You can fill this in. You can give a short statement on this. With maximum of 30 characters. It's very easy to join Slido, so you go to the website. You can also join from your phone, very easy. You go to sli.do, and there you will see the option to enter your code. You can type in CLIMA_HP. These instructions will stay on the screen on each slide, so you don't have to remember it by heart now. You can fill it in during the statements. I will first ask Volker if you want to come forward and give a brief statement on your vision on the markets, what's needed for the market uptake of heat pumps in Europe.
Thank you, Jasper, and thanks to everybody who spoke previously in the Tri-HP project for providing us a glimpse into the future. The question that I am asking myself is how soon is that future? Because this is the question we are asking ourselves in the policy environment all the time. So my name is Volker Franz. I'm Director General of EPI. EPI is a European association representing the value chain of the refrigeration, air conditioning, and heat pump industry. So we have the OEM manufacturers such as Daikin or Carrier, in our membership. And heat pumps are, of course, all the rage right now. If you attended this morning the keynote speech, then you know there's huge goals to accelerate the rollout of heat pumps, doubling the rate of installation of heat pumps in the next years. So we need 10 million additional heat pumps by 2027, 30 million additional heat pumps. We're only talking about air-to-water heat pumps here by 2030. So our modeling actually suggests that we need up to 60 million additional heat pumps by 2030 if you count in all the technologies. That's huge. That's staggeringly huge. So the question, of course, is how can the research community help to make heat pumps a commodity and not just a toy for rich people? And therefore, I mean, a lot of questions that Sylvain and Checo asked, I also had. How quickly can we go from TRL 3 to 5 to market readiness? That's going to be very important. And one of the key asks I would like to have in a potential follow-up project is precisely that, how to get the people on the ground who are actually able to install this and making it work and maintain it for normal people, because it's one thing to be a heat pump installer, it's another thing to be then an expert on the electricity system, combining it with in an optimal way with the electricity system. It's also in terms of propane. Yes, they are this is very important that you do that research because we really need it. There's increasing pressure from regulators to move towards natural refrigerants. But again, it's an additional challenge for installers. It's an additional challenge in terms of cost. The Commission has actually proposed now a ban for all monoblock heat pumps by 2025 with global warming potential, with refrigerant using global warming potential more than 150, and the market is clearly not ready for that. And if I understand correctly, there's not that much hope that the technologies you're developing will be market ready by 2025. That's an issue. So those were my thoughts that I was having. It's a run against time here. 2030 is tomorrow. It's less than 8 years, and by then we will have to have installed millions of new heat pumps. Everything that you can do to accelerate the practical applicability of your development will be very important. So in that sense, those were my final thoughts. Maybe at the end of the day, any of your research community might, I always look at the electromobility analogy, how to make electric cars a commodity. In a way, we need the same thing for heat pumps. So if anybody feels the vocation to create the Tesla of heat pumps, then please start doing this now.
Thank you, Volker. Let's hope so that we can get the new Tesla of heat pumps. Now, Josephine van Besselare from the European Heat Pump Association. I'll give the floor to you right away.
Thank you, Jasper. Thank you for the invitation, and also thank you to the previous speakers. Indeed, as also mentioned by Volker, it's very interesting from the Brussels bubble to have really a look into what is going on really in R&D and to see where the future is heading. And also I found the social analysis particularly interesting, and I was thinking, what if you would do this again now, this research with what is happening in Ukraine? I really think you would already have another perspective because you see people's minds changing on heat pumps. I have to say from a personal experience also, before not many friends were particularly interested in my job or in heat pumps, and now you see that they start asking, but these heat pumps, so what do they do? How do they work? Can I install one in my house? And even though before they were interested in doing something to combat climate change, now with this additional aspect of the war in Ukraine, you really see, I think, that this socially has another layer which creates even more interest in our technology. So I think that would be an interesting continuation of the research and the social aspect. So if we look at the current market, I can only repeat what Volker already mentioned. The targets that are put forward by the European Commission are huge. And as he mentioned, they have a target for hydronic heat pumps, so doubling annual sales in the next 5 years, arriving at 10 million hydronic heat pumps in 2026. But indeed, we need them all. We do not need only hydronics, we need all types of heat pumps. So extrapolating that ends up in 20 million heat pumps by 2026, even 60 by 2030. So our numbers are the same on that field. But how do we get there? Which measures are needed? Well, as EHPA, so we are the European Heat Pump Association, we really unite the whole European heat pump sector. That's manufacturers, also the national associations are a member of us, also research institutes, consultancies, test labs, and so on. So we have really 5 domains where we see that action or measures are needed. And a first one, a very important one, is that there needs to be created trust in a long-term ambition for heat pumps. This may sound a bit fluffy, but we really need technology clarity. So at the policy level, up to now, you very often had this principle of technology neutrality and always betting on different horses and never being very clear on heat pumps are really the way to go, that is really the future. And we really think that is needed. We need this clear signal both for consumers and for investors, for manufacturers, that they can put all of their investments and money in this technology, and that is the future. Because, for example, we have also members that are both producing fossil fuel, classic boilers, and then heat pumps. And as long as we do not get this clear political signal on heat pumps are really the future, the shift will not be made completely, also not by these manufacturers. Also, we need to make clean heating economically the most attractive. That's a very important one. We need a carbon price. We need a shift in taxes and levies from the electricity bill to the gas and oil bill. A third one, we need to avoid disrupting current market dynamics, meaning that revising legislation should not slow down the ambitious targets. So all legislation needs to go in the same direction. And there also I come back to what Volker has mentioned, the F-gas regulation. They should also keep in mind these targets that the Commission has set forward on this Repower EU communication. So you cannot have different legislations brought forward by the Commission that go in different directions. That's a contradiction, and this is really something that we need to make clear to them. So that's something we are working very hard on. Then it has also been mentioned several times today, the focus on skills for the energy transition. Even though we produce a lot of heat pumps and there could be a lot of demand, if you don't have the people to install them, well, you don't have them. So that's something we need to focus on. And then a last aspect that is very important also for you, for this community, is the R&D. We need continuous R&D improvements to keep improving efficiency, new technologies, and so on. So this intervention actually comes very timely because last week we had this Repower EU communication with these very ambitious targets, and there are quite some measures that the Commission already mentions in this document to tackle these things, but what we think is still really needed is a clear overall strategy to really bring the whole sector towards these targets. Like, for example, the Commission published an EU solar energy strategy, and we think we urgently also need an EU heat pump strategy, or accelerator, as they also call it. So that's what we are calling for. Thank you.
Thank you very much, Josephine. Then on to the last statement, Davide Sabadin, Senior Policy Officer at the European Environmental Bureau. I imagine you have something to say about the alignment with the F-gas regulation. Go ahead.
Thank you, Jasper, and thanks a lot to those who spoke this morning. Very, very interesting development, very interesting technologies. So the EB, for those who are not familiar, is the oldest and largest representation organization of the green movements, the green associations throughout Europe. So environmental association made of citizens, roughly 180 organization over 38 countries. So I'm following the F-gas, I'm following the eco-design, I'm following the energy labeling, I'm following all the everything related to heating and cooling in the policy-making arena, and of course from an environmental point of view. So let me start by the fact that I share many of the concerns that have been told about the fact that we need a clear direction. We also are in favor of some sort of heat pump strategy, which is not there, it should be there. And we also are in favor of clear indications. So, for instance, that hydrogen is not a future for heating, and heating should be electrified. And I mean, not only us, also the consumers have repeatedly given this advice. And we also are very worried about the massive training needs. We don't want to see this. We don't want to see what happened in some member states with other technology, groundbreaking technologies such as photovoltaics or solar thermals in the 80s, where there were not skilled professionals, and there was sort of it kind of backfired on the market. So there was a negative image of the technology because the first installers were not they were not really skilled. So we don't want to have this, and we think there's a need for immediate reaction throughout the European Union, not in 5 years, but now, really now, and it's not there. There's no sense of urgency from the Commission, nor in the Fit 55 package, nor in the Repower EU package. No sense of urgency on how important this training issue is. But as we're going for training, let it be on all refrigerants. So the good point is that because there are so few people trained on heat pumps, the good point is that when you're going to train them, you can train them also on propane and isobutane and the rest, because once you go for all of it. And the other thing is the energy cost. I mean, heat pumps are very efficient, but the upfront cost still remains an issue. So there are many member states where this support is not there. And we made an estimate before the energy crisis last year, and it turned out that having a simplified model with 10,000 euros cost for a normal family, only in 8 member states out of 28, the payback was lower than 8 years. I mean, on something that lasts roughly 20 years, we thought that 8 years payback time would be like something acceptable. More than that, it's more of a mortgage than it's like psychologically speaking. So. And that was because either you were missing upfront cost subsidies, or because the savings were not strong enough. Which brings me to the point that also Josephine made, we have to change the taxation. So the energy taxation directive has to be made in a way that if you use renewable energy, renewable electricity and heat pumps, you should be having like the lowest taxation possible, so that it makes sure that every time you use heat pumps in any country, you're on the safe side, that you're using the cheapest electricity option. And it should be there, at the very least, if you don't change the directive, it should be there as a sort of soft low option, so that you can go, and every utility in Europe should have this option, like a tariff for heat pumps that can make people make the change, embrace the change. And also a very important thing is that we're going towards a market where you have an ESCO scheme, so you're not necessarily selling the heat pump, you're selling the service, and so it's your interest to have the best performing heat pumps, and also to maintain the equipment properly. So that's for now only available for business to business market. It's really important that it goes to really to everyday market, so to the layman, to the laywoman. So we really have to extend this market. It's a key enabler. A few more points. I don't think that, we also agree that air-to-air heat pumps are important. There are some countries in Europe, around in the Mediterranean area, where there are millions of units of houses where you don't have hydronic heating. So what do we do to decarbonize those buildings? We need air-to-air heat pumps together with solar thermal and other technologies. And again, I don't think that the market is not ready. I don't think that the market is not ready. Why don't I think the market is not ready? I'm not a producer, so why would I say that? Well, for two reasons. First, because we have been asking the producers what they think. I mean, we have made a survey out of 50 major producers in Europe in last year, and 19 of them replied, 22 of them replied, 23, roughly half of them, and those who replied were also very important producers, and they clearly told us that they wanted to phase out the gas boilers, they wanted to phase out the subsidies for fossil fuels and heating, and that they're ready for the uptake of the market. On the other hand, we know that Wiesmann is investing 2 billion, only one company is investing 2 billion in the next years on natural refrigerant heat pumps. I mean, I think that they're going to lead and the others will follow. And this brings me to the point that it is true that today we don't have those heat pumps that are to be produced in 5 years, but everybody's investing. And while they are investing, they better invest in technologies that are future-proof, meaning technologies that are working on natural refrigerants. The reasons are, there are plenty of reasons, I will not go into details, but the point is that this is totally compatible with the F-gas regulation. To be honest, this is not a technical problem, it's a problem of the production line we have today. But the production line we have today are very small compared to the ones that we're going to have in 5 years, because if you want to deliver those numbers, there's no other way. So the new production line will be based on natural refrigerants. That's our estimation. And it comes from a climate point of view. We have to get rid of harmful refrigerants, and we have to be climate proof. Of course, there are safety concerns. Safety first is not something that we have to trade. But we think that, as someone else said, we have gas running in our homes and burning with a flame. If we manage to keep this safe, I'm sure we're going to manage to keep anything else safe. Thank you.
Thank you very much, Davide, for the good overview. Here you can see the results of the poll question. We're running a bit out of time, unfortunately, but maybe someone of the consortium, Thomas, maybe you could give a brief comment if the statements and the word cloud aligns with your experience during the stakeholder engagement on local level and EU-wide level.
Well, what can I comment on that? This perfectly reflects what we had in the interviews in the stakeholder workshops. So, and it has been mentioned before, also the three speakers, the commentators before, it was there. So yes, this apparently is a problem, and I would say, if you think about it, what is the solution? A lack of skilled workers. So if you read those recommendations that are there, it says we need better qualification, more qualification, qualify people, qualify heating installers better. But if I remember from the interviews, from some of the interviews, people were saying, well, it has been there before. There's programs and funding schemes and qualification incentives for heating installers. So maybe this is, if you want a solution to that, maybe you should go a step further and asking why is there, installers apparently up to now had no interest in taking that qualifications that has been there. So it's not only a question of incentives and giving the right incentives, but there has to be I don't know, change in the whole training system maybe. So this was also suggested in workshops and interviews. I don't know how this looks like, but if this is so urgent, I would think that incentives alone is not enough. So maybe I just stay with that comment.
Thank you, Thomas. Anyone else? Danny, maybe you would like to give a short response on the what you think of the does it align with your perception of?
Talking a bit what Thomas said about the lack of skilled workers and installers, I think there's probably a low interest of current installers to go and be educated in heat pumps because they make a lot of business with simple systems that they know how to work. They have a higher margin, so for them it's just more easy to do it, and they get more money out of it. So it is about money at the end. For them, they have more margin with what they have today, and I think this is a barrier.
Discussion is almost over, but maybe Josephine, maybe you can take the microphone over there.
Is it on? No.
Yeah, I think it's on.
Yes, it's working? Ah, okay. Yeah, I just wanted to add, so my previous job was actually at a national association where I was really in close contact with installers, and you saw there were two groups of installers. You had the ones already an older generation that said, yeah, why would we change? Like you mentioned, yeah, we are earning good money with the systems. They are simple to install. Everyone asks for them, so why would we change? And then you have a younger generation who is really more progressive and who wants to be like future-proof, green, and they really want to get educated, but it's really also a generational issue. And I also think, supply and demand, if people will ask, just clients, citizens will just ask more for heat pumps, well, they will have to retrain, so it's a bit, something. Yeah, I wanted to add this to the list.
Thank you very much, Josephine. I think we're going to have to round up here because I think we're around 10 minutes over time, and I can assume that people want to go to lunch. Thank you very much for attending our workshop. Thank you for all the expert inputs and the statements. And I wish you a very good lunch and a good rest of the day with nice presentations.